Dear learners, welcome to the course Disaster Management Strategies. As you know, Module 17 entitled Causes, Effects and Mitigation Measures of Flood, Earthquake and Landslide, consisting of 3 units. The second unit of Module 17 is Unit 35, Earthquake and Disaster Risk Reductions. Today, we will explore this unit together. I am Utpal Deka, your course coordinator from Krishnakanta Hendrik State Open University. I am excited to have you with me on this journey. Let's get started. In Unit 34, we studied floods, one of India's most frequent and damaging hazards, especially in river basins and urban areas. We examined their causes, devastating effects, and a mix of structural and non-structural mitigation strategies. Unit 35 now focuses on earthquakes, sudden, violent, and other unpredictable geophysical events that release enormous energy from within the Earth's crust. Unlike floods, earthquakes give almost no warning, strike instantaneously, and can cause massive destruction in seconds. India lies in one of the most seismically active regions of the world, with about 59% of its landmass falling in seismic zones 3, 4, and 5, that is high to very high risk. In this unit, we will cover definition and nature of earthquakes, major causes of earthquakes in India, primary, secondary, and transient effects of earthquakes, practical and evidence-based mitigation measures, including structural, non-structural, and community-based approaches, real-world examples, and lessons from major Indian earthquakes. By the end of this unit, you will understand why earthquakes are called silent killers and why building earthquake-resistant structures, enforcing zoning, and creating widespread awareness are critical for reducing risk in India's seismically active zones. Now we start with definition of earthquakes. An earthquake is a sudden and violent shaking of the Earth's surface caused by the abrupt release of accumulated elastic strain energy stored in the Earth's crust or upper mantle. This energy is discharged along faults, that is, fractures in the Earth's crust, when stress exceeds the strength of the rock, resulting in rapid displacement of rock masses. The released energy propagates outward in the form of seismic waves, which cause the ground to vibrate and can produce a wide range of destructive effects. The nature of earthquakes. The nature of an earthquake is instantaneous and unpredictable in exact timings, making it one of the most challenging hazards to forecast precisely. Earthquakes occur without warning, last from a few seconds to several minutes, and their effects can extend far beyond the epicenter due to the transmission of seismic waves through the Earth's interior. Earthquakes are measured in two main ways. First, magnitude. The total energy released at the source, measured on the Richter scale or logarithmic scale. Each whole number increase means approximately 31 times more energy. For example, magnitude 7 is 31 times more stronger than magnitude 6. Modern seismology also used the moment magnitude scale, that is MW scale, which is more accurate for large earthquakes and is now the standard in scientific reporting. Next, intensity. The observed effects at a particular locations measured on the modified Marconi intensity, that is MMI scale 1 to 12. Intensity varies with distance from the epicenter, local geology, and building quality. Now we will discuss key characteristics of earthquakes in India. India is located in a seismically active regions due to ongoing collision between the Indian plate and the Eurasian plate at a rate of about 4 to 5 centimeter per year. This convergence caused the uplift of the Himalayas and immense tectonic stress along the thrust faults. As a result, about 59% of India's landmass lies in seismic zones 3, 4, and 5, moderate to very high risk. We have already mentioned this. As per the Bureau of Indian Standard, that is BIS, seismic zoning map IS 1893/2016. India has experienced many devastating earthquakes, including 1897 Assam earthquake of magnitude 8.3, 1905 Kangra earthquake of magnitude 7.8, 1934 Bihar Nepal earthquake of magnitude 8.4, 1950 Assam Tibet earthquake of magnitude 8.7, 2001 Bhuj earthquake of magnitude 7.7, and several recent events in the Himalayas and Northeast. Earthquakes in India are particularly dangerous because many occur in densely populated areas with poorly constructed buildings, non-engineered housing, and inadequate enforcement of seismic building codes. Earthquakes are unique among natural hazards because they provide almost no warning time, typically only seconds between the initial P wave, that is primary wave, detection and the arrival of destructive S wave, that is secondary wave, and surface waves. Therefore, mitigation relies heavily on pre-disaster preparedness, earthquake resistant constructions, strict enforcement of building codes, public awareness, early warning systems where feasible, and rapid post event response. Unlike flood or cyclones, earthquake risk reduction is almost entirely about reducing vulnerability rather than controlling the hazard itself. Now we will discuss causes of earthquakes in India. Earthquakes occur due to the sudden release of accumulated stress along the faults, fractures, or weak zones in the Earth's crust or upper mantle. In India, seismic activity is driven primarily by natural tectonic processes with only rare and low magnitude events linked to human activities. India's location at the junction of major tectonic plates makes it one of the most seismically active regions in the world. First, we discuss the natural causes. First, plate tectonic movement. The dominant cause of earthquake in India is the ongoing collision between the Indian plate and Eurasian plate. The plate is moving northward at approximately 4 to 5 centimeters per year, subducting under the Eurasian plate and causing the uplift of the Himalayas. We have already discussed this. This convergence generates enormous compressional stress along the Himalayan thrust, faults, and the Indo-Gangetic plains. This tectonic correlation is responsible for the majority of high magnitude earthquake in North India, covering Himachal Pradesh, Uttarakhand, Jammu and Kashmir. Northeast India, covering Assam, Arunachal Pradesh, Manipur, Nagaland. Himalayan belt, including Nepal border regions, Andaman Nicobar Islands, subduction zone, faulting. Sudden slip or movement along pre-existing faults releases stored elastic strain energy, causing the ground to shake. Faults can be reverse or thrust, that is compressional, normal, that is extensional, or strike slip, that is horizontal. Major active fault system in India include Himalayan main boundary thrust, that is MBT, and main central thrust, that is MCT, known as primary zones of convergence in the Himalayas. Himalayan front thrust, that is HFT, which is known as southernmost active thrust faults along the Himalayan foothills. Kopili fault zone, Assam and Nagaland, which is highly active strike slip and thrust fault system. Koyna fault of Maharashtra, intraplate fault known for reservoir-induced seismicity. Next, Kutch fault system of Gujarat, which is responsible for the 2001 Bhuj earthquakes. Next, volcanic activity. Volcanic earthquakes are rare in mainland India today. The Deccan Traps volcanism ended 60 million years ago. However, low-level seismic activity occurs in the Andaman Nicobar Islands due to ongoing subduction and volcanic processes in the Andaman Sea subduction zone. Human-induced causes. While the vast majority of earthquakes in India are natural, certain human activities can induce low magnitude seismic events, usually with a magnitude less than 5, by altering subsurface stress conditions. First, reservoir induced seismicity, that is RIS. Filling of large reservoir increases pore pressures and stress on underlying faults, triggering small to moderate earthquakes. For example, the Koyna Dam in Maharashtra is one of the best known cases of reservoir induced earthquakes globally, with recurring earthquakes since the 1960s. Mining, quarrying, and large scale groundwater extraction. Removal of large volumes of material or fluid can cause subsidence and fault reactivations, leading to small induced earthquakes. This is observed in coal mining areas of Jharkhand and Orissa and regions with heavy groundwater pumping, high pressure fluid injections. Activities such as hydraulic fracturing or fracking, geothermal energy projects, or wastewater injections can increase pore pressure and induce micro earthquakes. Though rare in India so far, this risk is growing with expanding energy and industrial projects. Over 95% of India's earthquakes are caused by natural tectonic forces, especially the India Eurasia collision. Human induced earthquakes are typically small and localized. However, understanding both natural and anthropogenic triggers is essential for seismic hazard mapping, risk assessment, and a mitigation planning in high risk zone including 3, 4, and 5. Effective earthquake risk reduction relies on strengthening buildings, enforcing codes, and preparing communities since the hazard itself cannot be prevented or controlled. Now we will discuss effects of earthquakes. Earthquakes cause a wide range of destructive impacts that can be classified into three main categories. Primary effects, that is direct results of ground shaking. Secondary effects, that is consequences triggered by the shaking. And transient effects, that is short-lived or temporary phenomena. The severity and extent of these effects depends on several factors such as magnitude of the earthquake, depth of the focus, that is shallow earthquakes cause greater surface damage, distance from the epicenter, local geology. Sometimes soft soils amplify shaking through site amplifications. Time of day, for example, nighttime events often cause high casualties. And lastly, building quality and construction practices. First, we will discuss primary effects, that is, direct results of ground shaking. These are the immediate physical changes caused directly by the seismic waves moving through the ground. First, regional geological changes. Large areas of land may be uplifted, lowered, or subsidence, or tilt along the fault line. Crack and fissures. Visible cracks appear in the ground, roads, railways, riverbanks, and even hard rock surfaces. Displacement of land blocks. Sections of land shifts sideways, that is lateral, or up down, that is vertical, along the fault, forming fault scraps, that is steep breaks in the ground. Liquefaction. Saturated loess soil suddenly loses strength and behaves like a liquid, causing buildings to sink, tilt, or even float. This is very common in river valleys, reclaimed land, and areas with sandy or silty soils, sand balls, and mud balconies. Pressurized water forces sand, mud, and water to erupt from the ground in the form of boils and small mud volcanoes. River course changes or blockages. River may shift their path, becomes blocked, or form temporary lakes due to landslide or ground movement. Now we'll discuss secondary effects that is triggered by shaking. These effects happen as a result of the ground shaking and are usually responsible for the majority of death, injuries, and economic losses. First, landslide and rockfalls, especially common in hilly and mountainous regions. For example, widespread landslide during 2005 Kashmir earthquakes in Jammu and Kashmir and Pakistan administered Kashmir. Building collapse. This is the leading cause of death and injury in most earthquakes. Most fatalities occur when poorly constructed, non-engineered, or old buildings, for example, mud houses, unreinforced brick masonry, soft-story structures collapse. Fires, broken gas lines, electrical short circuits, overturned stoves, and chemical spills can start fires that spread rapidly. For example, significant fire damage after the 2001 Bhuj earthquake. Tsunamis, generated when the earthquake occurs under the sea or displaces large volumes of water. For example, the 2004 Indian Ocean tsunami, triggered by a magnitude of 9.1 to 9.3 earthquakes of Sumatra, which severely affected the Andaman and Nicobar Islands and coastal Tamil Nadu. Dam or embankment failure. Shaking can cause dams, reservoir, or embankment to crack or breach, leading to sudden downstream flooding, a major risk for Himalayan dams. Disruption of utilities and lines. Snapped power lines, broken water, and sewer pipes, damaged telecommunications tower, and destruction of roads, bridges, and railways severely hamper rescue, relief, and recovery operations, as well as development process. Transient effect, that is short-lived or temporary effects of earthquakes. These are temporary phenomena that usually disappear soon after the shaking stop, but can still cause panic and lead to secondary hazards. First, perceptible ground tremors, ongoing aftershocks, and continued felt shaking of buildings, bridges, and towers. Panic, fear, and psychological trauma, widespread fright, and post traumatic stress among survivors, especially children and vulnerable groups. Disturbance to animals, unusual behavior in birds, livestock, and wildlife. For example, birds suddenly flying away, animals running in circles or trying to escape. Temporary changes in groundwater, sudden rise or fall in water levels in wells, springs, or ponds due to pressure changes in underground aquifers. Swaying of tall structures. High rise buildings, poles, towers, and hanging objects may sway noticeably even during the moderate shaking. Primary effects, that is, shaking and ground rupture, starting the damage, but secondary effects, including building collapse, landslide, fires, tsunami, usually cause the greatest loss of life and property. Transient effects add to immediate panic and can trigger additionally accidents, for example, frightened animals causing chaos. In India, the overwhelming majority of earthquake, death, and injuries result from the collapse of poorly constructed buildings. Now we'll discuss mitigation measures for earthquake risk reductions. Earthquake risk reduction in India focuses on minimizing vulnerability through a combination of structural safety measures, land use planning, early warning systems, public awareness, and community preparedness. Since earthquakes cannot be prevented or predictable with exact timings and locations, mitigation efforts emphasizes reducing the impact through resilient constructions, regularity enforcement, and proactive planning. The Bureau of Indian Standard, that is BIS, seismic zone mapping as per IS 1893 Part 1 2016 serve as the current official seismic zoning map of India. This map classifies the entire country into four seismic zones 2, 3, 4, and 5 based on the maximum considered earthquakes, ground motion, and expected severity of shaking. It replaced the older 5 zone system, that is 1 to 5, used before 2002 and remains the mandatory standard for earthquake resistance design of buildings and infrastructure across India. Now let us discuss non-structural, that is long-term measures. Earthquake hazard zonation and microzonations. National and local seismic zonation maps identify high-risk areas across the country. Microzonation studies, which is assess local soil type, ground amplifications, liquefactions, potential, and site-specific shaking, guide urban planning, land use decisions, and building regulations. Critical facilities such as schools, hospitals, emergency services, buildings, and lifeline infrastructures must be located in lower risk zones wherever possible. Building codes and seismic design standards. The Bureau of Indian Standard mandates earthquake resistance design through key codes. IS 1893, that is criteria for earthquake resistant designs of structures. IS 4326, that is earthquake resistant design and construction of building, and IS 13920, that is ductile detailing of reinforced concrete structures. Core design principles include ductile detailing to allow controlled deformations without sudden failure, avoidance of soft story mechanism, strong column, weak beam concept, use of base isolation and energy dissipation devices in special structures, retrofitting of existing vulnerable buildings. Next, public awareness, education and training. Widespread information, education and communications campaigns, integration of earthquake safety into school curricula, regular mock drills and community training programs build preparedness. The Appadometro scheme trains community volunteers in basic response skills. The internationally recognized drop cover hold on technique is promoted as the standard immediate response during shaking. Early warning systems. India is actively developing earthquake early warning systems similar to Japan's model. Sensors detect the first arriving primary waves and issue alert 5 to 60 seconds before the arrival of destructive secondary waves and surface waves. Pilot projects are underway in Uttarakhand, Delhi NCR, and parts of the Northeast, with plans for nationwide expansion. Now we'll discuss structural or engineering measures. First, earthquake resistant constructions. New buildings in zone 3, 4, and 5 must incorporate seismic resistant features such as reinforced concrete frames, shear walls, steel bracing systems, and flexible foundations. High weight roofing materials and elevated plinths help reduce structural mass and inertia force during shaking. Retrofitting of existing building. Older, non-engineered and vulnerable structures, especially schools, hospitals, heritage buildings, and multi-story residential blocks are strengthened using techniques such as column and beam jacketing. addition of shear walls and bracing, base isolation and dampers, foundation strengthening and soil improvement. Next, infrastructure protections. Critical infrastructure such as bridges, dams, power plants, water supply system, communication towers must follow stringent seismic design standard. Redundancy, that is backup systems, fail-safe mechanism, and seismic qualifications of equipment ensure continuity of essential services during and after an earthquake. Now we will discuss integrated and community-based approaches. Land use planning and regulation first. Construction is prohibited or severely restricted in high risk zones, especially near active faults and liquefaction prone areas. Setback rules from fault lines and guidelines for development in soft soil zones are enforced through town planning, authorities, and building bylaws. Community preparedness. Local communities are trained in search and rescue, first aid, fire safety, and family emergency planning. Village level disaster management committees, relief camp identifications, and pre planned evacuation routes ensure effective response. Regular community drills and awareness campaigns build confidence and reduce panic. Post disaster reconstructions. Reconstruction follows the build back better principles. New structures are built stronger and safer than before. With relocation from the high risk zones where feasible. Seismic safety is integrated into recovery plans, ensuring that rebuilt communities are more resilient to future events. Earthquake risk reduction in India relies almost entirely on reducing vulnerability rather than controlling the hazard itself, as earthquake cannot be prevented or accurately predicted in real time. The most effective strategy combines strict enforcement of seismic building codes, retrofitting of existing vulnerable structures, land use regulations, early warning where possible, widespread public educations, and community participation. In a country where 59% of the landmass lies in moderate to very high seismic zones, including zone 3, 4, and 5, and millions live in non engineered housing, these measures are essential to save lives and protect property during inevitable future earthquakes. Dear learners, in this unit, we started by understanding that an earthquake is a sudden shaking of the earth caused by the quick release of built up energy deep in earth's crust. We learned how earthquakes are measured using the Richter scale for magnitude, that is, how much energy is released, and the modified Marconi intensity, that is MMI scale, for the effects felt at a particular place. We then looked at the main causes of earthquakes in India, the ongoing collision between the Indian plate and the Eurasian plate, which creates huge stress along the Himalayas, major fault lines, and other regions. These tectonic movements is why so many strong earthquakes happen in northern India and northeast and parts of Gujarat. We also explored the different effects of earthquakes, such as primary effects, that is, direct damage from shaking, such as cracks in the ground, land shifting, liquefaction, and changes to rivers. Secondary effects, that is, problems caused by the shaking, including building collapse, landslide, fires, tsunamis, dam failures, and broken utilities. Transient effects, that is, short-lived issues like aftershocks, panic, fear, unusual animal behavior, and temporary changes in water levels. Finally, we studied practical ways to reduce earthquakes risks, such as seismic zonations and microzonation, strict building codes, and earthquake-resistant designs, retrofitting old buildings, public awareness, and Lastly, community preparedness. India faces very high earthquake risks in many areas, especially seismic zones 4 and 5, and most deaths happen because of poorly built structures collapsing. That is why the most important actions are enforcing earthquake resistant building codes everywhere, retrofitting old and unsafe buildings, teaching everyone drop cover, hold on, and how to stay safe, preparing communities with drills and plans. Your role is to advocate for earthquake safer buildings, participate in drills, and promote awareness in your community. Earthquakes give no warning, but awareness, preparation, and resilient construction can save lives. Thank you for completing Unit 35. In the next unit, that is in Unit 36, we will learn about landslide and disaster risk reductions. Stay alert, stay prepared, stay safe, and resilient. Thank you.